Hello and welcome to our video case study looking at forward focus CAN. Now this is some CAN network errors that flag up for multiple reasons. You'll often have U codes when you do a vehicle scan with no real fault or symptoms. Well, in this case study we'll look at what those events are and how they happen. I'd like to look at scan tools as well, because scan tools will give them very different descriptions for the same fault code. Some are very helpful, some not so. We'll look at something called receive error counts using a third-party decoder, and then we're also looking at the decoder in Picoscope and how we can manipulate that using Picoscope, of course, and with Excel as well, so Excel skills will come into play here. And then finally, just the effects of impedance on CAN networks. This case study looks at a momentary interruption of the CAN impedance on the network, so we just lose one resistor momentarily, and the havoc it creates, especially when this fault occurs for longer than, let's say, half a second. So I do go on a bit, but enjoy. Forward focus with a CAN issue. So these are those dreaded scans that you do on a vehicle where you get multiple CAN codes in various systems, and to just go through the CAN codes, we've got ABS that's reporting multiple CAN error configuration codes. Then we've got the engine ECU that's reporting loss of communication with ABS. Instrumentation that's reporting loss of communication with engine. And then to top it all off, airbag reporting loss of communication with the instrument panel. So if you put all that together, you'll be replacing 1, 2, 3, 4 components there at crazy cost for a car that's worth no more than a handshake. So where do you start and what tools have you got at your disposal? Well, of course, Picoscope's in there. It's got to be in there, looking at the CAN physical layer, the voltages on the CAN network. Based on all those fault codes, it's a network problem, but where is there a component that's responsible for all of those? And how do you decipher which one of those components it is? We'll also use a logger. We'll look at CAN logging, seamless logging outside of Picoscope to see if the two tools can tally and give us more direction. Learning or working with this car, it highlights also the issues you have with scan tools as well. So various scan tools, they all present the codes, but then give you various descriptions of that code. Some better than others, as I'll describe as we go on. But of course, everything starts with CAN resistance check, and we'll demonstrate that in the next video. So one of the fundamental checks we can do with CAN is at the 60 ohm test, and luckily with this vehicle we've got 60 ohms at the diagnostic connector because we can get straight onto the CAN. We don't have to go through a gateway module. So on the road, this vehicle would play up. You'd often see multiple messages coming up, warning lights. So to try and simulate that, we'll graph the resistance of the 60 ohm CAN network. And how we'll do that, we'll use the Pico breakout box. The vehicle battery is disconnected. We're only using the breakout box as a pass-through, purely for convenience. And we'll start moving the vehicle. So if we were to rock the vehicle backwards and forwards, bouncing, moving the wiring harness and connectors, and then if we tap the fascia here, just look at the resistance, how the resistance is changing of the CAN network. For every tap of the fascia, actually, we get a change in CAN resistance. If we give it a real good play, well, there you are, it won't do it now, but we've actually seen that go from 60 ohm to 120 ohm, suggesting that we're losing the termination resistance within the instrument panel. Picoscope 7 on the left, we've connected to channels A and B with scope probes, so high impedance probes, and they're connected to the CAN network, CAN high and CAN low. High impedance because we don't want the measurement tool to influence the network in any way. Underneath we've got the decode table, so when this buffer is either stopped or we reach the end of the buffer, we will update the decode table with the data captured in the physical layer. We can only update at the end of the buffer or when stopped because we are in streaming mode. On the right hand side we've got vehicle spy, and that will be monitoring the CAN bus simultaneously. So we'll have seamless logging here from vehicle spy, and we'll have the physical layer captured with Picoscope. We'll introduce a fault. Tap the instrument panel on this car can actually introduce a CAN fault, and we'll demonstrate how both softwares capture this event and how we can attribute the event to the actual impedance and voltage levels on the bus. So let's turn ignition on. Okay, and just focus on the decode table first of all within Picoscope. So notice that when we reach the end of the buffer, then we can decode and we update the decode table. We're looking for anything red to appear here. That will denote that we have an error in a packet. You will often, or you may see, buffer number 1 or packet number 1 is red. That may be simply because the data was streaming through at the start of the buffer and we only caught that packet of data halfway through, and often results or can result in an error. So often buffer or packet 1 and the final packet in a buffer may well come back as red, failed to decode. Over here we've got vehicle spy scrolling. We've got the scrolling view, or we've got the fixed view there, whichever you prefer. What we'll do is we'll have it scrolling because I'm going to introduce a fault now by tapping the instrument panel, and we'll hopefully capture in both softwares. There we go, and it didn't flag an error at that point. Let's try once more. There we go. So we'll pause here and we'll pause there. Now, Vehicle Spy says there's a high-speed CAN error being detected, and that will be denoted with a green radio button. So within there, there'll be an error flag. There they are. Let me just get back there. Okay, we'll keep that on there. And also there'll be an error captured in Picoscope. And the quickest way to find the error in our decode table is to, there we are. Now I'm hoping it was this buffer. It could have been this buffer as well. Alright, so there's a number of errors. We'll match them up in a later video, but let's just double click on, let's say, this packet here, because it didn't transmit any data. In fact, see this red area here? So what packet number that is. And that's another error on the CAN bus, which we'll talk about later, but that bleep is from the instrument panel, which is now lit up like a Christmas tree, and engine malfunction is just displayed. Let's just double click on here, and I think it goes without saying we can see that there is huge disruption to the physical layer there. Yeah. Let's actually go full screen on that for a second. And right, so here we see that we have normal messaging. Let me zoom in. So that was a perfect CAN message if we were looking at the voltage levels. And then let's scroll along to the next message, and we can see that disruption there. So the physical layer has gone high, and there all kinds of chaos going on there before the buffer is restored, before the bus is restored, sorry. Okay, looking at that closely, you can see that CAN low and CAN high have been driven up to 3.5 volt. So in which case, no communication can take place. So multiple errors there. Let's just go back to Vehicle Spy. And what is Vehicle Spy reporting? Let's go full screen there and have a look at the explanations. So we see something here called REC, that's receive error count. And I'll just go scroll up. Alright, so it starts here at final message that came through and decoded accurately was 231, ID 231. Then we start receiving error counts 9, 10, 18, and then they start decreasing. As they decrease, we start to get other messages coming through. So Vehicle Spy is displaying the errors in such a way as to inform the user that receive error counters are being increased within nodes, within control units on the CAN network. We'll talk about that in a later video when we correlate this data. We'll show the decode table in Picoscope against the decode table in Vehicle Spy, and then hopefully make full sense of what's going on. But what we can safely say here at this point in time is tapping the instrument panel introduced a change in the impedance of the CAN network, such that we ended up with this issue here with the voltage levels going to 3.5. So both CAN high and CAN low, see there, have been driven to 3.5 volts. Referring back to buffer 30 then, this was where we captured the error, and you can see the errors here, this red area highlighted in the graph view. Might be worth just going back one buffer and seeing where these errors started. So we go back to buffer 29, we are decoding on the current buffer only, so whatever's in this view here. And to see if we've got any invalid buffers, we can click on this here and order by invalid. Let's go to buffer 30. Now ordering by invalid, there you are. You see it's listed 925 to 978, so I think there's 8 in total there are in error. And moving on to buffer 31, it has found one here, and why is that? Let's double click on that and that will take us straight to the packet of interest. You can see there that we haven't captured a full packet, and the zoom overview demonstrates that. So if we just try and pull this out here, notice that we're right on the end of the buffer. So that is a valid packet, it's just that it's come back as an error because it's incomplete, and that is not our fault. We need to go back to what is our fault, and that is the fault condition on buffer 30, and it's these areas here. So they seem to be closely grouped. So if we go by start time, so 105, 1 second, sorry, let's go to about 1 second, yeah, 1.005, and then this all ends at 105, so we'll go around about there, yeah. And if we zoom in, we should be able to see where these events took place, and there they are. We can see where the bus has been pulled high, so there's one incident there, a second incident and a third incident. And if we look at the time span of these, so that was our last valid transmission, and then we've got 1, 2, 3 events, and then we start decoding properly probably round about there. So we are there at 38 milliseconds. So within that 38 milliseconds there, you can see that the CAN bus was driven high 3 times. Let's just zoom in on one incident. There it is. And from a customer perspective, there was no fault at this point in time. Although the CAN errors were present, there was no fault, no symptoms at all. The system had tolerated these faults, no doubt had tried to resend a message that hadn't got through. But there was a point, if you remember in the video, where the alarm sounded. That was the instrumentation. Unfortunately, I got both apps paused at that point in time, so I didn't capture the event, but that's when the CAN bus would have been driven high for a long period of time, such that all transmissions would have been halted, and then of course multiple warning lights and multiple errors. So let's now correlate this data here with what we got in Vehicle Spy and see if we can see where the sequence of faults begin and where they end, and what happens in that interval of a fault condition. Picoscope 7 and Vehicle Spy side by side now, so we're now going to correlate the data that's been streamed through, so the decoded data in Picoscope with the data that's streamed in Vehicle Spy. Vehicle Spy is in simulation mode, so this is playing back a recording of all the data captured from the incident where banging the fascia introduced CAN errors. So if we want to jump to the area of interest in the fascia in the decode table, double click in the graph view and then zoom out, because we're looking for the very first incident of our CAN bus being driven high, and it looks like it's this one here. We'll place a ruler on the last message that was successfully transmitted, so that was the end of the message. And to find out what that message was, if we double click on that, it jumps to that message in the decode table. It's 231. And I will scroll up a bit because we need to correlate this data. So ID 231 was the last message that got through before this incident of the CAN bus going high. And we move now to the next successfully transmitted message, which was 190. So between those two incidents, we've got 3.719 milliseconds, and there they are. So a successful message, a CAN error, and then another successful message here. So there's the gap, and the next message was 190. Let's just zoom in just to clarify that. 190, there it is. You'll find actually if you hover over the frame, you'll be able to see the message. There it is, packet 926, and the data as well. So with 3.719 milliseconds between those events, let's have a look at vehicle spy. So there's the last successful message to ID 231. And then the next one is 190, which we've confirmed here. And in between there, then we have REC, which is receive error count. And these are being incremented up to 18, and then they start to decrement. So it appears that during that period of time, in fact, 3.034, if we just come back a little bit, 3.034, I'll say roughly about there. In that period of no transmission, it would appear that nodes are storing and recording in the controller, in their respective controllers, error counts. Now we can't see that in Vigascope at that point. Now we move on to 190 message which comes through, and that was this one here. And that is a successful message. Another notification that the error counters are decrementing, which is great, because 430 message gets through, and that correlates here. And these continue then to decrement because the bus, in effect, now has been restored. There was this momentary event here, and now we've got a good physical there. So as you can see, during that period of time, successful transmissions from all nodes, and successful receipt of those messages as well. So as a result, these decrease. A bit more information about the error counters within the CAN controllers. We saw here that 231 was the last message that got through. Then we had these errors here. And note the error counters start to increase as we described. The fact that these are green suggests that the error is active. In other words, the node is still allowed to participate, still allowed to communicate on the network, flag errors, and terminate messages that it feels are in error. Now, as we scroll down, that state changes. First of all, it does increase, and then we start to get successful messages coming through as we described, and the count dropped to 0. Then the bus was restored here. Then all of a sudden the count starts to increase dramatically, and the ratio of these increases differ depending on the condition. So transmit errors, they will increase at a different rate than receive errors. Also notice there are no transmission errors, suggesting that no ECU is sending an error transmission. Above a certain level, I thought it was 127, but on this it's at 91. You see that we started to turn our errors into red. Now this suggests that the node has changed state. It's moved to error passive state. So it can still flag errors, but it cannot terminate messages. So it can still notify of errors, but not destroy the message on the bus. This increases, and then it looks as though everything is starting to come right again, and then we decrease. And what I wanted to show here was I'd matched up. Let's just quickly go back to the beginning, 231. I'd matched up the final good message, so 231 here, And then if we scroll down to the very end, where we go from error passive back to error active, where it's green, and then eventually this count keeps coming down, where we finally get to receive error 0, and then the bus is back to normal again. And I've done that here. So the last message here was 190, and there it is, and they do match. 0055, 00003C, 03003C. And it was just the time that it elapsed. So if we look, I've now decoded between the rulers, so rather than decode all data, I'm only decoding from the last received message, good message, to the point where our error counters reverted to 0. And that amount of time was 163.5 milliseconds. So although the bus was restored and everything was fine at this point here, because there was our last event, look, of being driven high, error counters are still active and counting down. So it is good to know that there's additional information beyond what we see here in Picoscope, because we are decoding at a silicone level when we actually decode with Vehicle Spy. It's all valid information, and I'll look now at an event that happened on the road, and I showed you a brief capture of this video earlier, and this is where the bus was completely offline for a considerable amount of time, and we'll compare the error counts with those events to what we can see here. What I'd like to show here is the fault that occurred on the road, where this would result in the network shutting down momentarily, and warning lights on the dashboard with an error message of I think reduced power. At this point in time, I was scoping both networks, so we've got CAN high and CAN low, and VAN high and VAN low on this car, so vehicle area network, which is a low speed network. And the instrument panel is the gateway for these two networks, so any exchange between the two is handled by the instrument panel. And the point to note here is that the VAN network is consistent when the fault occurs in the CAN network. So if I zoom in here, where we see the bus go high, just notice how that the VAN is completely normal, so the bus on CAN has been driven high, but VAN is normal. Which again makes you stop and think, can we actually say this instrument panel is faulty at this stage? Maybe the CAN controller could be within there. Also Vehicle Spy, that can do both networks at the same time. So you'll see here you've got high-speed CAN, and then you'll see high-speed CAN 2, and that will be the second network. So these are the messages coming through, and they are in order of arrival based on their speeds. You'll notice here, look, that there are far few messages on VAN by comparison to CAN, because this is a lower speed network, so fewer messages. What I'd like to do now is remove some of the signals from this capture and add in the maths channel A minus B, because when we get this kind of noise, what we want to do is see exactly what the engine ECU, or sorry, the CAN network, the controllers are seeing in terms of differential voltage. So we'll bring back A minus B, and this is 0.2 volt. And we can see during this period of when the CAN bus was driven high, how there was some form of communication still ongoing. Because the network was down for so long, it's approximately 2.5 seconds. So if we go from 2 there to 4, let's say 4, yeah, 2.5 seconds approximately. That was enough to send the error counters sky high, as we described earlier. And you see here, we've got receive error counter 255. When it gets to that level, that is what they call bus off state. So that node is now, or nodes are off the network and are prevented from transmitting. They are isolated.
And normally for those to be restored, it's a case of removing the power supply, ignition on, ignition off. But for some reason here, that did not happen on the road, because this was a momentary event, quite lengthy in terms of CAN, 2.5 seconds. But then it starts to decrement. So it's a bit of a confusion for me as to why that happened, but nevertheless, the fact that it's now back online and decrementing is what's happening right here. The bus has been restored. So one to note, when you see that 255, technically that should be a bus off state for the controller or a number of controllers. Now, looking at the decode here, I've opted to add some more decoders because there's some interesting information during the fault condition. Let's take away A and B now and just focus purely on the CAN network A-B. I want to zoom in to this area here. And if we keep zooming in, it becomes apparent that there is messaging going on here. Now, I've used the decoder here between the rulers, so let's just come back out so we see those time rulers. There they are. I'm just decoding this area here, and we've got areas of very low voltage and areas of where almost transmission is restored. Not quite. I mean, you can see there that that's not correct. So let's have a look at that, because it does intrigue me. And I have decoding on it. Now this one here is 0 fault. So I've used 0 as my crossing point in the decoder. And if we keep zooming in, it reveals ID 275. ID 275 appears to keep transmitting through that fault condition. Okay, so let's have a look then at this area here. So this is the decode at 900 millivolts. So I've chose to a crossing point of approximately 900 millivolts. Let's say about there. Let's click on here, and this is suggesting, hold this up, that ID 80 and 200 are attempting to decode during the fault condition. So we've got 80, let's pull this up, 80, 200, 80, 200, I think there was 280 in there as well. So there's 3 IDs that are trying to communicate during the fault condition, which certainly suggests they're not offline at that point in time. So food for thought there, and maybe further diagnostic information. Going back to those previous captures, it would appear that transmission was ongoing during the fault condition, and we'd ID'd a number of IDs, and that was 80, 200, 275 and 280. Now, what we could say was that those ECUs were transmitting, and that got me thinking, what could they be? Because if they're transmitting, if they're online, then during that point in time, maybe they are not responsible for that condition. So remember the ID with the lowest number as the highest priority. One way of trying to understand which IDs belong to which computer is to disconnect that computer and then run a capture and then separate all the IDs. And that's what we've done here. So we've got test 30 ABS ECU disconnected. So this is simply ignition on, capturing CAN data. We're not worried about CAN fault here, just CAN data with the ABS ECU offline. And be careful when you do this, because if you disconnect an ECU with a termination resistor inside, you are going to change the impedance of the network. So you may have to insert a 120 ohm resistor. As it so happens, that doesn't occur when you disconnect the ABS ECU on this vehicle. So how do we go about doing this? How do we ID IDs? So we use the export feature, and we'll export this to a folder. We've already got it here. We'll do it again. Test 30 ABS ECU disk. yes, we want to replace that. And now I'll bring in an Excel sheet here. I've already got a buffer here. This was test 10 with error fault buffer 30. This was a capture I did where all ECUs were connected. So I know that all the IDs on here are relevant to the whole network. What we want to do is pull in that second sheet. So we want to pull in data from CSV, and it was test 30 ABS ECU disconnected. And we'll load that. And we'll save ourselves a bit of space here because we're not really interested in min-max voltage there. So we'll highlight this column here and we'll paste it over here. So these are all the IDs where the ABS ECU is disconnected. Now we're going to click on this column and remove duplicates. My data does have header. It's going to leave us with 17 unique values. So those are all the IDs that were online when the ABS ECU is disconnected. And let's actually give that a proper name. So we've got ID ABS discon. Right, let's copy. Bring that across to this spreadsheet here and paste. We'll now do the same for this column. Copy. I'll paste that over here. Now we should theoretically have more IDs here if we do the same thing, because on this column here, these are IDs where the network was complete. So continue with the current selection. My data does have headers. And there we are. We can see that there are a lot more IDs when the ABS ECU is disconnected. So theoretically, the difference between the two must be linked to the ABS ECU. So if we highlight both of those, and I think it's on the Home tab, Conditional Formatting, highlight cell rule, duplicate values, and then we can ask it to highlight unique values. Click OK, and there we go. So these unique values are 80, 90, 20F, 211, 4BO, and 212. Now, in some ways, they are linked to ABS ECU. Remember, lowest number, highest priority. Now, 80, we did see being transmitted during the fault condition. So it suggests to me, at this stage, that the ABS ECU was online during the fault condition and was making attempts to transmit. Now 275, yeah, 275 is there. That was trying to transmit, but doesn't appear to be linked to ABS ECU. 280, yeah, and 200 as well. Okay, so we haven't really identified those, but we know that 80 is most likely linked to ABS ECU. If we minimize that and go back to the screen, we can do something similar with Vehicle Spy, because we can just list in fixed order. So those are the IDs that were present on the network when the ABS ECU is disconnected. There's something I want to show you here, I want you to be aware of. We're running simulation now, so this is just the network traffic that was present. Notice a couple of IDs have appeared there, And if I keep running this for a little bit longer, you'll see that more IDs will appear. There we go, 40 and 46. So I'm going to pause that there and bring back the Excel sheet. See if we can right, ABS ECU disconnected. Note here that 46 certainly and 40 do not appear here. And for that matter, they don't appear here. So be aware of that condition, because these would appear to have a very slow pole rate. In other words, they're not sent out that often on the network. And it could also be that these have been transmitted because ABS is offline. I'm not sure about that. So I just want you to be careful that when we use picoscope, we did a sweep 500 millisecond divisions. But these IDs here, they appeared to be transmitted very slowly or at a very slow pole rate. And it could be that in a sweep, where you looked at CAN traffic with your ABS ECU disconnected, these weren't present simply because they weren't captured, they weren't transmitted during that time span. So with Vehicle Spy, we were able to leave it running for a long time, seamless logging. Alright, I hope that helps.
One last word on the diagnosis before we move on to the fix, and that is scan tools and just how they present data. And of course, on the right we've got Bosch. It's a very good tool, very good generic tool. It's just how we actually list fault codes and present additional data. And here we can see a number of unknown CAN communication faults. If we focus on the ABS U1900, pretty much that's as much as the data that we have on the Bosch side. Yet if we look at the same fault code on 4Scan, which I admit definitely is a dedicated scan tool for that vehicle, we just get far more. And this is in the review, and there's some real good clues to our initial fault, knowing now what we know from the previous videos. This one here, CAN communication fault, receive error. We've talked about receive error counts. Again, receive error. This one here, the ESP module has not received the correct message from other modules on the CAN communication data bus. This as well, no valid CAN communication or messages received for over 500 milliseconds. We've seen that in the videos when we've measured the physical layer as well. I like that there, that CAN communication data line that are not communicating and are timing out. The timing out would refer to those ECUs that their receive error count went up to 255, so they would be bus off. Yeah, of course, there's some suggestions there about short circuit and open circuit in the CAN. But also this one here, this killer line, do not replace the ABS module based on this DTC alone. How true is that, knowing what we know now? Not knocking scan tools at all. Absolutely, having a generic tool is a great one-stop tool, get you by. But I do like these dedicated tools, or tools that offer this additional snippets of gold, if you like, when we're diagnosing. So the cause of all this carnage with the CAN network was poor termination of the pins at the instrument panel. You know, hitting the instrument panel or the binnacle would result in a change in the CAN network resistance. So if you look closely here, these are the pins that pass through from the connector on the instrument panel into the printed circuit board, and hopefully you can just see there's cracking around there. Also the pins that come through, the solder is separating there. We almost get like a cone around the pin but no contact with the pin. Now post-fix, this is what they should look like after the solder's been reflowed, and AC Tronics have done a marvellous job here. They use a technique called vapor phase soldering, I think it's called, where they heat the instrument panel PCB up and reflow the solder. But as you can see here now, no cracking around the pins, so this is post-fix. Pin contact with the solder as well. And these are taken, I'm not sure if they're under a microscope, but they're certainly zoomed in. Their machine is here,
So this is the machine in question. So the printed circuit board will go into there from the instrument panel. It will be heated and the solder reflowed, which means we end up with good connections throughout the printed circuit board. More information on their website as well. Here we are, Vapor Phase Technology. Also a video describing the technique. And of course they've got this instrument cluster documented quite well as the faults to expect and the repair process. So thank you AC Tronics, hope that helps.
So thanks to the team at AC Tronics, the instrument panel has come back, it's been fully refurbished, and it leaves nothing really other than to do the resistance check first of all. You remember using the Pico resistance lead, how we tapped the instrument panel and we were changing the impedance of the network. At times it was 70 ohms, 80 ohms, occasionally 120, so a complete open circuit. And then we'll run CAN, so we'll start decoding in Picoscope, tap the instrument panel, try again, see if we can force this error, and monitor with Vehicle Spy as well, looking for CAN errors, receive error counts. So far so good. I'm quite pleased. This is a fix. We'll just run through videos now to demonstrate.
So here we have the refurbished instrument panel from AC Tronics. Thank you guys. And the first test of course is the Pico resistance lead. So it's BNC plus resistance lead into our CAN breakout box and then into the diagnostic connector. So there's our pass through. And then what we need to do is bang the fascia. So the battery's disconnected. This is just purely the 60 ohm test. See if I can get a better view here. And keep your eye on the graph view there from Picoscope. That seems to be great. Let's see if I can try and capture how the dashboard is bouncing or how the instruments are bouncing. Needless to say, that line is rock solid at 60 ohms. Okay, so with the new instrument panel in, we've got D9 connector here through to 16 pin. We've broke off there with the scope probe so we can get into Picoscope to look at the CAN physical layer, and then the value CAN from Vehicle Spy. That's also connected. Our software is running. We've got Vehicle Spy on the right and Picoscope on the left, and we'll run through ignition on cycle and just see if we get any error counts. So we'll wait for that to come round. Ignition on. And so far so good. No error counts there. Bottom right hand corner Vehicle Spy. And if we pause Pico and we go back right at the start there, quite often you may see an error here or no acknowledgement, because often ECUs wake up at the wrong time or different times. That is all good. So we look for an acknowledge. Oh, let's go full screen here. Or valid and invalid. No, there's nothing. So everything decoded successfully there, which is cool. And now of course let's try the tap test. So this is where we were hitting the instrument panel as we are here, and we're looking for errors generated, and I think that's been a little bit ambitious and aggressive. Nevertheless, proof is in the pudding. We'll pause Pico there, we'll pause Vehicle Spy, and we'll look at both. So starting with Picoscope, yeah, we have one error there. That's interesting. Ah, there we go. That's right at the end of the buffer. We are missing the full packet. So that's the reason for that error. Let's just check that again. Yeah, it is packet number, let's have a look, 1064, right at the end of the capture. Let's zoom in so we can actually see the signal. Yeah, we haven't completed the packet. If we hover over that, we should be able to see, yeah, sorry, excuse me, 1604. Yeah, okay. Let's go through the others. So this is now decoding for buffer 4, and if we decode on valid, any failures to acknowledge. No, that's all good. Let's go back through them all. In fact, if we go all buffers, this will present us with the entire buffers, also all 5. And let's look for valid. There's 1, and it was that one there again. So the only one that failed through the tap test of the instrument panel was the one that we'd stopped, or where we'd stopped the capture midway through the packet. Okay, so coming back now to vehicle spy, what did that detect? No bus errors. And we can scroll back through here. The last 50,000 messages. And we're all good. No error counts. So I think we can conclude that that is a fix. Thank you again, team at AC-Tronics.
So there you have it, a refurbished instrument panel has resolved the concern we had on the CAN network. I hope it goes some way to show you the tools at your disposal when it comes to intermittent CAN errors. I guess you could argue this was a documented fault. They're quite well known for this issue. If you have a look on the AC-Tronics website, they've got this well documented. But coming back to intermittent CAN errors, what tools have you got? Well, Picoscope, of course. Hop onto the CAN network, start decoding, drive the vehicle, as you saw in one of the earlier videos, how we lost communication entirely. Next was wiggle testing, or in this case, it was hitting the instrument panel. We could momentarily generate CAN errors, receive error counts that we captured with Vehicle Spy. So a couple of tools, well, 3 really. You've got the resistance lead, or graphing resistance, which is better. You've got Picoscope for serial decoding, and you've got seamless logging with a logging tool. We happen to use the value CAN. Intermittent errors, I mean, they are so difficult, aren't they? Especially with CAN. The best you can do is opt for something like a slow time frame, 200 millisecond divisions, where you can actually see the graph drawn in real time. Perhaps use 2 apps at a time, maybe 3 apps as well. Maybe you have a camera open, maybe you have your logging, so you've split your screen, got all that on one screen, and then road test, because once you capture the event, pause all the softwares, pause the camera, save all the data, run back through the video, and then you can start to correlate the video footage and then open the files accordingly. So options that we've got for these intermittent CAN errors that can drive us insane. I hope it helps, and yeah, thanks for watching.